Okay, hi everybody. I think we're back. I think I'm finally live. Sorry, I was checking out the new streaming system I have here, and it's not streaming to the right URL on my channel, but it is streaming to my channel, just not to the URL I told it to. So you will find it, and you guys will make it over here through the course of the Hangout. I am streaming, however, to Dr. Brian Keating's channel, so it is working on there just fine. So
Hey, hi everybody.
we are back.
Finally live. Sorry, I was checking out the new streaming system I have here, and it's not streaming to the right URL on my channel, but it is streaming.
There we go. I had too many URLs open. Sorry about that. Okay, so wow, it's been a while, so I'm a little bit rusty. I want to welcome you guys back to our little Hangout series. This is something we try and do every Friday, well, many Thursdays, with Dr. Brian Keating, who also has a channel which is located. The link to his channel is located in the description box below. And I want to today we're going to be talking a little bit about the Nobel Prize season that is upon us now. This is October. This usually is the time when people start talking about the Nobel Prize in everything. So I'm gonna bring Dr. Keating up here in just a minute. In the meantime, I want to let you guys know I am streaming on both Dr. Brian Keating's channel and Deep Astronomy. So please chat and leave your questions in the chat box, and we will get to them. So let me bring Brian up. Are you there, Brian?
I'm here. Can you hear me, Tony?
I can hear you loud and clear. So welcome back. Finally. It's been a while, and crazy. So a lot of stuff happened in the course of my streaming adventures, but hopefully we'll be back on track. So, Brian, this is Nobel season, right? This is the time when the Nobel Committee starts announcing their Nobel Prizes, and we have several of them that were awarded this week. And the one I think that we're the most interested in here today is going to be the one that was announced in the physics category. So you want to describe to us a little bit about what that was? And you've interviewed some of these winners, or at least one, I know.
Yeah, I know very well Sir Roger Penrose. In fact, he has started a project called the Penrose Institute, and they want to have that really to be hosted at UC San Diego, where I am, of course, the Chancellor's Distinguished Professor. You know me as not super distinguished, but I am the Chancellor's Distinguished Professor of Physics.
You're super distinguished for sure.
No, I try. And I know Andrea Ghez very well. She's a friend of UC San Diego. She's a mentor and a friend to many astronomers in my research groups, kind of orbit, so to speak. And that's a pun that was intended because, of course, she received it along with Reinhard Genzel for discoveries related to tests of not a black hole. Did you read the description? It didn't say, proving a black hole exists. Rather, it said for evidence for a compact, massive object at the center of our galaxy. And that was very cleverly orchestrated by the Nobel Committee. I have to give them, some years there's good prizes, some years there's questionable prizes. This was certainly a great prize all around, especially, not the least of which because it went to a close friend who blurbed my book. I mean, how often does that happen when a Nobel laureate blurbs a book about losing the Nobel Prize? But he's just an incredibly gracious and wonderful individual. This was the prize for black holes. And there were many related kind of issues and topics that we can get into. And I also had the pleasure a couple weeks ago of talking to one of the pioneers, modern day kind of young guns that are looking at not only black holes, but possibly wormholes, and wormholes that you could travel through. So you and I, Tony, could finally meet and we could be in person together through a wormhole for some live stream that we do someday down the line.
Oh, I would love that. The one thing that I don't think a lot of people realize is just how recent it is that the observational evidence for black holes are. I mean, we've theorized, they've been theorized since the late 18th century, but with mathematicians bringing them up as mathematical constructs. But it really, I think the EHT, the Event Horizon Telescope, was the first that really definitively said, there's one. There's a black hole. We've actually seen it. Of course, Einstein came along and said they should exist. And of course, we've seen a lot of indirect evidence for black holes. So is it this idea has been around for a while, but is it because we've only recently gotten observational evidence of black holes that these guys,
Yeah.
maybe the Nobel Committee recognized what they did?
Yeah, someone asked me earlier, as I get asked pretty frequently, who's going to win the Nobel Prize every. I call this the Annunciation season. I think of Nobel Prizes as kind of a religion, and
Yeah.
this season has been the season of Annunciation, and then the coronation season happens not on Alfred Nobel's birthday, but on his death day, which is December 10th, which is basically a national holiday in Sweden, and
I
that
love
will
how you
be.
call it a coronation. We'll get to that in a minute.
So Annunciation Week, I get asked all the time, and I actually predicted that Black Hole Project would win it this year. I didn't predict my friend Sir Roger would win it, but I did predict that I thought the Event Horizon Telescope would win it for imaging the event horizon around a black hole, which is
Yeah.
as close as we really have come. So the Nobel citation for Gez and Genzel, my one of whom is my colleague within the University of California system, is cited for the compact object, and that's relevant because if you look at the actual citation, they talk about because the reason is you really can't say for certain that this object is a black hole, and even so, the case is similar in the Event Horizon Telescope. You're not actually seeing a black hole. And
Right.
what
Well,
you're
you
seeing is
can't.
sort of the influence of a black hole, right? And in fact, somebody mentioned, if you replaced the sun with a one solar mass black hole, we would miss its light, but we would keep orbiting around as we are, and we'd have a 365 and a quarter day year, just like we do now. So it's really not commensurate to say that they discovered a black hole, but in reality, they did discover something very, very compact, and that has an effect on the orbits that is consistent with another Nobel laureate's predictions, although he didn't win it for this, and we know that as Albert Einstein. So it's really a confirmation of that that these two won it for. And then Penrose is sort of controversial in the sense that his citation reads for discoveries relevant to general relativity, and really using it as a vehicle to understand relativity. But again, he's done tremendous work along with his late great colleague Stephen Hawking, who I met a long time ago in person, but never had a chance to get him on the podcast, unfortunately. But his predictions were really related to the discovery of consequences of general relativity, which of course relates from Albert Einstein.
So that was his contribution, Penrose's contribution. What about the other two? What were they? What was their contribution? And I just want to point out, before you do, I want to say real quick that you said the EHT did not directly see a black hole, and you're right, but that is about as close as we're ever going to get to seeing a black hole, is to see its event horizon, because nothing can come out. You're always going to sort of infer their existence on the things around them. And this is something immediately around M87, which we did see. And Galaxia brings up the point, I put up that chat there, that we can also see the stars revolving around Sagittarius A star. That's the supermassive black hole at the center of our Milky Way, is also an inference of a black hole being there. So Roger Penrose did a lot of theoretical work predicting what you should see based on Einstein's relativity, and that was his contribution. I know I'm oversimplifying, but then the other two, what were they? No, what did they do? What were they?
Right.
What were their contributions?
You're exactly right. So one of the things that's important to realize in science as experimental scientists or observational astronomers is that we can't really do an experiment where we would make a black hole in the laboratory, play around with it, see if it has certain properties that are expected. We can't visit a black hole. We can't have a black hole interact with the sun. These are not experiments. Scientists like us, we cannot do experiments where we have cause, isolate, control, variable, etc., like you learned in high school. Instead, there are classes of discovery that we rely upon that are called indirect or direct. What I study is potentially the indirect evidence for gravitational waves from the ultra early universe if the universe underwent a period of extremely rapid inflation. That would produce, as a consequence, indirectly gravitational waves, which would then imprint the cosmic microwave background radiation, imparting onto it a type of polarization that we call B-mode polarization, this twisting, curling, rotating pattern of polarization that was the subject of my book, Losing the Nobel Prize. And instead, there are experiments like LIGO, which can make a direct detection, wherein a gravitational wave comes into their laboratory, perturbs it, makes certain objects longer amongst one direction, a perpendicular direction shorter, and they can measure that distortion, characteristic distortion, in direct fashion. So that's a direct experiment. And similarly, most astronomical experiments and evidence for particles, for fields, for forces like gravitational waves are only indirect at best. So what these two scientists did with their huge teams is they used something called adaptive optics, which is a technology co-invented by a very, very famous astronomer, also in the University of California system. Her name is Claire Max, and others pioneered a system that is colloquially said to freeze the atmosphere, to make the atmospheric distortions due to turbulent fluctuations of the atmospheric water vapor content, that roiling fluid that we rely upon to breathe and to live, creates havoc for astronomical observations. So what they did is develop a technique that could freeze it, and then the pioneering work by Gez and by Genzel's teams, what they did is apply that in the infrared, and that gets not only rid of the atmospheric fluctuations, but also contamination from that scourge of Nobel Prizes everywhere called dust. So they were able to use infrared adaptive optics over decades to trace the orbits of stars, of actual stars, honest goodness stars, around an invisible spot of matter that was inferred to be a black hole. And so that's what they did. They indirectly demonstrated the existence of a compact object, which has all the properties of a black hole, different from the properties of a massive object in three major regards that we can get into. But these contributions are really applications of technology and observations over decades. And that's what allowed them to kind of make these predictions of what you'd see and compare that to what relativity predicted.
Yeah. So you mentioned something when you were explaining that I kind of want to dive into these days about the way science is done, and that is that these are the recipients of the Nobel Prize in physics for their work, but they are by no means working alone, right? I mean, these are huge. In many cases, especially with gravitational waves, you can't just use this equipment all by yourself. I mean, this has to come with huge collaborations. Does winning a Nobel Prize, I mean, as these guys did, but they're part of a much bigger team, does it reflect on how do others feel about it? I guess is my question, because are people being singled out for any reason? I mean, I don't know what the algorithm is. I'm sure there is one for deciding on what a Nobel Prize is, who gets it. But is there any
there's no hard and fast
being left
rule,
out or any of that?
That's sort of what my book concerns, is that the Nobel Prize is a human process. It's not like there's some law of nature that says this person and that team deserved a Nobel Prize. It's highly capricious. It's very selective. Usually they get things right in the physics prizes. You can question how well they've done in the other awards, although there have been some bloopers in the Nobel Prize in physics too. Don't forget Niels Bohr won the Nobel Prize for basically a proposition that the atom is basically a tiny solar system in the early 1900s, and we know that to be completely wrong. Of course, he made some other contributions, as you know, in the Copenhagen School, which some question. But despite that, and actually Enrico Fermi, who is a titanic physicist of the 20th century, his Nobel Prize was really incorrectly attributed to the process that we now call fusion, but really he was describing fission. So that was a blooper in a certain sense. They got that wrong. But he also is widely respected, and certainly many believe that he did deserve it. So in the physics prize, I would say it's the least of the blunders and blooper variety. On the other hand, all Nobel Prizes suffer from the effect of exclusion and leaving out these huge teams of people that without which make the project impossible. It happens to be that there are no other prizes that are as prestigious. There are prizes that pay a lot more. The Breakthrough Prize pays perhaps 10 times as much if you win it by yourself, and can include the entire team. and I know I've received, I can't divulge their names, but when LIGO won, there were three people who won it. I talk about this in my book, how one of the co-creators of LIGO, Ron Drever, passed away just a few months too soon to have been considered for the Nobel Prize in 2017.
So it's not given posthumously then, is it?
They have given it posthumously twice to Swedish people, to Swedes and the literature and peace prizes, but they have never given the physics prize posthumously. They've given the medicine prize posthumously. They changed the rules in 1974 to disallow posthumous prizes, and technically that would mean even if you die the minute before the ceremony, they wouldn't give it to you. There was a case about 9 years ago when a physician was announced to have won the Nobel Prize, but when he was announced, he had already died. They ended up giving it to them. Now, the issue with posthumous prizes is only took place in 1974, and someone like Rosalind Franklin, therefore, was eligible to win the Nobel Prize posthumously because there were no preclusions against it. She died in the late 1950s, I believe. And Watson and Crick and Wilkins won the Nobel Prize for DNA's double helix discovery in, I think, 1963. Or so, maybe 62. Someone can correct me in the audience. But she was eligible back then because they didn't change the rules for another 12 years. So I've gotten into fights with the Secretary General of the Nobel Academy, Swedish Royal Academy, which awards this, about this online.
Really?
We had a flame war. I could put a link to that in the chat, and maybe people will find that interesting.
Well, yeah, definitely, yeah. So you're fighting with him about this. Well, that's good.
Yeah.
I think it's hard for something like this to not get politicized, or certainly emotions run pretty high with who gets the Nobel Prize and who doesn't. And in fact, if I remember right, please correct me if I tell this story wrong, but Albert Einstein did not win the Nobel Prize for his work on relativity. He won it for his work on the photoelectric effect, which is the science that all of our solar panels are based on. But did he receive that much later than people thought he should have got it? I mean, it was well into his life, right? By the time he got the Nobel Prize, Albert Einstein.
It's so interesting because he did receive it in he received the 1921 Nobel Prize, which wasn't awarded until 1922 for some reason. It wasn't because of a war, etc. And he won it, as you said, for the photoelectric effect, not for special relativity, not for general relativity. Special relativity was predicted by him in 1905. General relativity was predicted in 1915. So there were 7 years, or maybe even 17 years between these two different discoveries, which had been borne out. Now, why was this a problem? Well, it turned out that you're eligible to nominate winners of the Nobel Prize if you previously won a Nobel Prize. Now, who was winning Nobel Prizes in the early 1900s when Einstein could have been eligible was mostly German scientists, Austrian scientists, Eastern European and some Western European scientists that were deeply anti-Semitic. In fact, Hitler had a cadre of what he called Aryan scientists explicitly working to prevent people like Albert Einstein, who was considered to be practicing Jewish science, which meant theoretical science, like Philip Lenard and others who discovered the photoelectric effect. Real men, real Aryans did experimental work. Theoretical work was beneath a real physicist. It's funny because I am an experimentalist and I'm also Jewish, so I probably wouldn't have been too fond, or they wouldn't have been too fond of me back then. But the point is, he was precluded. Now, who won the Nobel Prize between, say, 1905 and 1922? One person who won it was a man, Norwegian or Swede, named Gustav Dalén. Now, what did he win it for? Well, he won it for the impeccable creation of a type of lighthouse regulating buoy and gas accumulator that regulates the pulsation of lighthouses. He won that in 1912, 7 years after Einstein's special relativity. Now, I don't know about you, but I usually navigate using not GPS, which relies on general relativity for corrections, but I use lighthouses and buoys whenever possible. So that certainly has had a beneficial effect on me. No, so there wasn't any. Yeah, exactly. So there's all sorts of politics. I always point out, as happy as I am for the winners, as much as in the past, I certainly wanted to win a Nobel Prize, and people say I'm a hypocrite or I have sour grapes. This is a prize mainly determined by the whims of about 400 Swedish scientists, 90% of whom are male, and how representative is that? Now, they often get it right. I think that they did a great job. in this year's selection, especially because a woman was selected for only the fourth time in history. And one of my friends was joking, "Look, you're having an impact. Your book, which says that all these women have been left out, just since my book came out, 2 women have won it. We've doubled the number of female winners just since losing the Nobel Prize came out." So I take full credit for that, of course. Just kidding.
Yeah. Well, it is true. They have been wildly underrepresented. In fact, treated quite unfairly throughout the process. So, how much time do I have with you, Brian? Do you have to go early?
No, I can go for another 15 minutes.
Okay. Can you stay till maybe 4?
Yeah,
or maybe another half an hour. Okay, because I want to go back to black holes, and then I want to go back to this because I have some other questions. I've been doing a lot of reading about science, scientism, and a lot of areas that make science less accepted by the general public than it used to be. And one of the things in the course of my research my reading that I've come across is this idea that when we talk about black holes are by definition a singularity. They are these regions where gravity has gotten so strong that they are regions of zero volume and infinite density, and up to a point, the laws of physics operate within the guidelines of general relativity. We go towards a black hole, space-time is curved extensively, and then we reach a point called the event horizon, which is this point beyond which we don't know what's going on. Our laws of physics can't help us with goes on with the other side of this event horizon. Do you think that's a problem for physics, and relativity specifically? If you've got something in your theory, and this is my question, if you've got something in your theory that contains singularities, like black holes, these are infinities in your math, isn't that a problem for the theory? Is it incomplete? Is there something that is it like Newton's framework, where things are right in a certain regime, but then they stop being right, and then relativity takes over? Is there something like that going on here, where relativity is right in a certain regime, and then beyond that, it does not work very well? I mean, are black holes a problem?
Yeah, you're absolutely right. And this has an influence on something else that you're deeply concerned about, which is theories of everything. So you could ask the question, as you and I have talked about it almost 2 months ago, I can't believe it. But, do we need a theory of everything? Some would say yes, because the laws of physics have to obey these symmetry principles, and because the forces of nature that are shorter range and higher strength than gravity are all manifest in a quantum domain. They all have quantum mechanical bosons that mediate the forces that kind of bind together the particle players, the actors in the grand scheme of quantum mechanics. But gravity refuses to be quantized for reasons that we can get into, and that we have no evidence for the quantum of gravity called the graviton yet. But what if we ask the question on the other hand, as you're saying, the two domains in which you might demand, if you're greedy, a theory of everything have to do with the behavior of gravity near singularities or n singularities. So first you have to ask the question, are singularities real? What if you found out, God hands you a letter and says there's no such thing as a singularity? We assume there are singularities because, as you say, these properties of black holes seem to demand the breakdown of classical. That means, the equations of general relativity break down at the very, center, the zero radius point from the concentration of mass that we would call the Schwarzschild metric. Now, but what if, and the other domain rather is in the early universe, if the universe began in a singularity, right? Those are the two regimes in which you might expect or demand there to be a singularity and an explanation of that. So those should be, fairly common to people. But I always point out, is there an example? Tony, can you tell me an example of some place, some phenomena that is infinite in strength? Are you there, Tony? Tony, can you hear me? I hear myself. I see myself. I think Tony is frozen. So I'll keep talking and hopefully Tony will come back online. If you're out in the chat room, can you please let me know if you can still hear me in the chat? I don't hear Tony. He appears to be frozen, like he disappeared into a black hole. But I can hear myself and I see myself. Tony's frozen. Okay, I'm going to keep talking. So consider, if you will, in the chat room, tell me an example of some place where there's an infinity of a physical quantity, not a mathematical quantity, not, 1 divided by 0 is infinity. No, instead, a physical quantity. The temperature at the center of the sun is not infinite. The density at the center of the sun is not infinite. How do you go from something that is infinite, truly infinite? It has a 1 over 0 in the physics of it, the density, the temperature, the matter content, that then suddenly tapers away from infinity of time. Or now it seems like I have disappeared from Tony's channel, but now I see Tony. Tony, are you back?
Yeah, I am back. Yep, we should be here.
Okay, I was there. I think I am still there.
Yeah, sorry about that. My computer, but that's a good test. The stream went on, which is great.
The stream
that's
continued.
Awesome. Even though I died, so that's great.
So I made the joke that you were frozen as if you had just disappeared beyond the event horizon of a black hole.
That's what it would look like, wouldn't it?
Exactly. So I asked you before you broke out, is there an example that you can think of a physical quantity that is infinite? Anywhere in the laws of physics that you understand, not singularities, not black holes, but tell me, so what if there is no such thing? Then do we need a quantum theory of gravity? I would say maybe not. The other place it comes up is in as in the beginning of the universe, if the universe experiences a singularity. But as we've talked about, we don't know for sure if the Big Bang was a singularity. And it has certain suggestions made by people like Paul Steinhardt, the Albert Einstein professor of natural science at Princeton, and Neil Turok and others, that the universe is cyclical. Roger Penrose, let me just say, I don't have to quote Paul Steinhardt. I can say Nobel Prize winner has a theory where there's no inflation, there's no singularity, and that's called the conformal cyclic cosmology. And I have an interview with him on my YouTube channel, which you should subscribe to, Dr. Brian Keating, on YouTube and on Twitter. Find me there. And if you do that, you will find interviews where he talks about the predictions that we would see if the universe doesn't have a singularity. So now we're having, very questionable considerations. Do we need to have a singularity? Are they really physical? And nobody knows for sure. So I always ask the question.
Well, that would help then. That would really help then with relativity if we did not need one, right? But then it begs the question: what the hell are black holes then, if not this? So.
Yeah, black holes are these mysterious objects where relativity, is so wildly unpredictable and almost anything goes, and that can happen in the early universe if the Big Bang took place in the singularity as well. But we don't really have, I would say, what if we may never have evidence for the singularity, as you say, and what if there are other, the question is, can you have the black hole signatures that we do see? In other words, how they affect them, the stars that orbit around them, as Gez and Genzel imaged, or if they have the properties that LIGO can measure, the spin, their charge, their magnetic fields, perhaps. How can they be used to test the properties of general relativity and reveal whether or not we need a quantum description of gravity? Which brings us, maybe, if you're willing to go there, to my conversation with Juan Maldacena at the Institute for Advanced Study, which is the house that Einstein built, like Babe Ruth built Yankee Stadium. And maybe we'll go there, because I think your viewers and my channel will really appreciate this. I had a conversation with Juan Maldacena, who is widely considered to be, maybe second only to Ed Witten or people like that in terms of the brilliance at the Institute for Advanced Study. And I've been lucky to be able to get interviews. I'm trying to get Ed Witten, and maybe I'll start a write-in campaign from your listeners and my listeners. He's never really done a podcast, but so too, Juan had never done a podcast, and he is very famous in physics community and outside of it for really considerations that revolve around extra dimensions, the properties of the early expanding universe, something called anti-de Sitter space, and what's called conformal field theory. These are really abstract but very, very fascinating instances of physics at extreme behaviors in the early universe, and near wormholes. And of course, the question of whether or not a wormhole exists is a totally open question. What Juan Maldacena attracted my attention for recently, and why he agreed to come on my show, was because I noted that he had produced several papers. He is really looking at whether or not the properties of a wormhole could sustain travel through space effectively faster than the speed of light or at extreme velocities, and could be transportable of the human body. In other words, they would have a diameter which would support the traversal using by a human being, perhaps in some kind of a tube or spacecraft or something like that. So he looked at the implications of that, and he started out with some really powerful and interesting ideas of a friend of mine by the name of Lisa Randall at Harvard, who wrote a wonderful book called Warp Passages, in which she talks about these extra dimensions. And she had discovered, or she had predicted, along with a colleague, Randall Sundrum, I believe he's at the University of Maryland, and they had predicted this possibility for these extra dimensions, which we would call large extra dimensions. And the large extra dimensions would create the properties that would be potentially conducive for gravity to have both long range forces and, in some sense, be able to be unified with quantum mechanics in a sense that I can get into. But the topic, I just put that at least in my channels live chat. I don't know. Can I just paste it into your channel? How do I do that? Just paste it.
Yeah, should be able to.
Yeah, okay, I'll try that. Send you a message, restream. No, that's the help thing. There's a chat box on the right.
You can't do it from the. Oh no, you can't do it from this app. You got to do it from.
I can't do it from the app. Oh, that's too bad.
Yeah.
From the YouTube channel. Okay, that's fine. Yeah. I'll do it later. I put in my thing. So what Randall and Sundrum came up with was that you could have these large extra dimensions. In other words, the universe that we inhabit has 3 spatial dimensions, 1 time dimension unified by Einstein into what we call space-time, 4-dimensional space-time. But what Randall and Sundrum proposed is that they noted the following thing. If gravity is very weak, but because it's so weak, it propagates across the entirety of the universe in a way that, say, the strong nuclear force, the weak nuclear force cannot. And they said, well, what if there was an extra dimension that we can't really perceive in the 4th dimension any more than a creature living in the 2nd dimension could perceive what it means to go, on a sphere or something like that. They can understand maybe what a circle looks like, but they couldn't understand a sphere. Maybe we can't really comprehend it in terms of physical manifestation. But what if there was an extra dimension, a 4th spatial dimension, and that dimension could be located, say, near us in a certain sense, that you could have a circle on a piece of paper on the table, and then you could have a beach ball, just a few inches away, and they couldn't perceive each other, and there would be an existence of an extra dimension where the beach ball could propagate into the 2nd dimension and reveal itself, as this famous book called Flatland talks about, one of the most influential books in my life, which I'm planning to do a special episode about soon. But getting back to this,
Edwin Abbott.
She predicted. Yeah, Edwin Abbott, that's right. So Randall and Sundrum predicted, well, there could be a 5th dimension, a 4th spatial dimension that's close to us in some abstract sense in this 4th spatial dimension space, and from there gravity could leak from the 4th dimension to the 3 dimensions that we inhabit, meaning that it could propagate across the entirety of the observable universe potentially, and that's called the Randall-Sundrum cosmology or Randall-Sundrum space-time. And what Maldacena did is he said, in such a universe, what would the properties of quantum mechanics be like? And basically, he found that there's certain ways that you could unify the gravity of the 5th dimension with the quantum mechanics of the 3 dimensions that we inhabit, in which case you could spontaneously create this wormhole, which would allow the propagation instantaneously, effectively, although the particle itself wouldn't get transported back in time. It could go travel macroscopic distances in microscopic amounts of time, so that at some level it could be propagating essentially as fast as the speed of light or faster, even though it has mass, which is normally precluded in the understanding of special relativity that we understand. A massive object like you or I cannot travel at the speed of light without an infinite amount of energy. So this is very fascinating to me. Do I believe it? Absolutely not. There are all sorts of problems with it, not the least of which is we have no evidence for the fifth dimension. So how could it be that you rely, and this, by the way, this only works, you can only make a human traversable wormhole. You could make a wormhole where a particle could transmit itself through. So microscopic wormhole. Theoretically, you could do that in 4 dimensions, but it's not clear if you could do a large macroscopic, say 1 meter diameter, a half meter diameter wormhole that a human being could traverse. Now, I don't see Tony again. Can folks let me know? Am I visible still in the 4th dimension? Tony seems to have disappeared. Can someone put in the chat if you can see me? I'll keep blathering on about my conversation with Wald Maldacena. If you do indeed see me in the chat room, I still see myself. I see myself. Yeah. Okay. Tony is crashing it. So what's interesting to me is that what Professor Maldacena is saying, but I do in that there are these traversable wormholes. Sorry, Tony, we lost you for another few minutes.
I know. This is a brand new laptop, and it keeps crashing. I have to completely reboot. So
but don't worry.
Sorry.
Don't worry.
Anyway,
yeah,
I was listening to the point up to the gravitational waves leaking through space-time, and then I was gone. So unfortunately, I didn't get to finish what you completely said. But don't say it again, because I don't want to force people to have to hear a repeat on it. But sorry about that.
What's so interesting about what Maldacena and I talked about is that it actually connects together, this kind of entanglement between particles that Einstein and Rosen had talked about way back when. But what's so fascinating about these wormholes is that they do seem to require this extra dimension. And there's no really essential reason that we would have to believe that a 5th dimension is necessary, except possibly to unify gravity and quantum mechanics. But again, Wolfgang Pauli, I think he originally said something like, who ordered that? Like, why do we need to have this unification of gravity and quantum mechanics if they're only possible to be manifest at singularities where we have no evidence that singularities exist? So I found it very interesting, these Nobel Prizes, the conversation I had with Juan Maldacena, and the properties of black holes. Now, which of the Nobel Prizes is sort of near and dear to my heart? It's really the observation and of these orbits of stars, because that's mechanics, Tony. That is the application of the laws of mechanics, of orbits, at some level of Newtonian mechanics, not even relativity. Only the very closest stars that they imaged for decades. But it's a story of perseverance. It's a story of using massive telescopes. It's a California story. It's a University of California story. And it's also a story of a woman who's persisted against, kind of extreme odds. You think about, Tony, I didn't know this, but Vera Rubin was one of the first women to ever get allowed to observe with a massive telescope, in this case, the Palomar 200-inch telescope. And it was only in the late 60s and early 70s when she was allowed to observe it, and she didn't have to pretend that she was married to an astronomer. She was actually a titanic figure in astronomy. And only 50 years ago, she would have been forbidden. And now we've got the first woman, to win a Nobel Prize for essentially observational astronomy, and the persistence that she had, and the technical tour de force that her group really emboldened and demonstrated. I'm very happy about that personal side.
Yeah, and I didn't know that either. It's funny, nowadays what we look at as a socially acceptable way of doing science is really rather recent. It is even in our own lifetime, mine too, that things have changed so much. All right, I want to go back to the Nobel Prize thing for a minute, because Roger Penrose was one of the awardees today, or this week. And I was reading, I want to see if I can bring this up. Hopefully I can. And this is, I was reading Ethan Siegel today, and he published this article on, get my cursor. And he published this article about, I guess, with Roger Penrose definitely, here's the article, by the way. It's on Forbes, and he wrote it today. He definitely deserved the work he got, things like that. But I want to read this part here. He goes, unfortunately, Nobel laureate Roger Penrose, although his work on general relativity, black holes, and singularities in the 60s and 70s was absolutely Nobel worthy, has spent a large amount of his efforts in recent years on a crusade to overthrow inflation. Okay, by vastly promoting a vastly scientifically inferior alternative, something called conformal cyclic cosmology. And I don't want to go into what that is, only the point that he was making here towards the bottom of the article is this paragraph here. While we should laud the creativity of Penrose and celebrate his groundbreaking Nobel-worthy work, we must guard ourselves against the urge to deify any great scientist or the work they engage in that isn't supported by the data. In the end, regardless of celebrity or fame, it's up to the universe itself to discern for us what's real and what's merely an unsubstantiated hypothesis, and for us to follow the universe's lead, regardless of where it takes us. And this reminds me of the part of Einstein's life where he was spent a great part of it also looking for a theory of everything. And so my question to you is this: does winning the Nobel Prize, do you think, give you a sense that anything you think is worth listening to? Because in the case of certainly this CCC model of trying to get rid of inflation, it seems almost like a willful disregard of what the data are showing us about. The observations certainly support inflation. And to what extent do you think this bleeds over? This idea of winning I'm a Nobel Prize winner. To what extent do you think it goes into your science? Obviously, it makes you famous, but does it make you a better scientist as a result of having won it?
No, I mean, oftentimes I talk about in my book, Losing the Nobel Prize, it has an awful, degenerative effect on the collaborations that led to the Nobel Prize in the first place. As I said earlier, I didn't maybe finish it, but the Nobel Prize for LIGO, I get emails from people that are disgruntled that they weren't even mentioned, they didn't get a penny, that if they did a tremendous amount of work, they should be recognized. And so it tends to distort the way that science is actually historically presented. In other words, you go back and you say, well, Kip Thorne and Barry Barish and Ray Weiss, they were the three founding pioneers. And in fact, there was another person, and Barry Barish only came along later. And he's actually a friend and a great scientist, obviously. But he came along after Ron Drever, had declined in health and so forth. But what you're talking about is called the halo effect. And it's a form of bias called authority bias, where you think of somebody as an authority in all things because they're expert in one thing. For example, Einstein was asked to be the first president of the state of Israel in 1948. But he knew nothing about politics. I mean, he had some really kind of dumb ideas about politics and anti-nationalism and kind of things that led to, and I'm not criticizing him. It's just in retrospect, being a pacifist wouldn't have played out so well in World War II. And so I think he has similar ideas. Now, you'll also get the effect that sometimes you'll get all these Nobel Prize winners will come out and say, you shouldn't sign a treaty with Iran, or you should vote for these people. Every year, this year, 77 Nobel laureates told us that we should vote for Joe Biden. Now, what does someone who won a Nobel Prize in 1968 know about in condensed matter physics, know about current politics in the global scene? No, they're clearly only getting attention because they won a Nobel Prize. And that's part of the idolatry of Nobel Prize winners that I talk about in my book. And look, I suffered from it too. Early in my career, that was a huge motivation to win a Nobel Prize, because I think when you lack, other kind of outlets as I did maybe back then, or want to achieve this level of fame and authority, that's the surest way up the ladder. Now things are different for me. But getting back to what Ethan said specifically, look, he criticizes most things. He's a very oppositional, very contrarian thinker. What Roger has done is he's done something very valuable in the conformal cyclic cosmology and made it such that inflation is not a monopoly. And whether or not I don't believe necessarily in the conformal cyclic cosmology, but to have things like Ethan is proclaiming that he's doing damage to science by talking about the lacunae, the problems in inflation, I think that's outlandish, and I think that Ethan is way off base there because
I don't think
it's
he's
very
saying that. I don't think he's saying that so much as he's just uh, uh, putting forth a the justification for why he says this is working is it depends on how you look at the data, for example. And I'm trying to I can't find
Well, he's
the
saying
quote
some
anymore,
blandishment,
but
that the universe will tell us what the answer. Look, the universe doesn't tell us anything. We don't get like
well
a
that was
signal
his well that was his
from Jupiter, right? We
oh,
get data, and so what Roger has done is he's made a prediction. It happens to be his predictions have been way off base, and I've actually challenged him about this in person. There are consequences that he calls Hawking points that he says are present even in the Bicep 2 data. And then I've personally disabused him of when he's come to San Diego. As I said in the beginning of the podcast, he's a friend of mine personally, and he's trying to have the Penrose Institute at UC San Diego, in part at UC San Diego. I've talked to him about the many problems with the conformal cyclic cosmology proof, so to speak, from the Bicep data, which is something I'm very expert in understanding. So I am saying he's predicted something that's falsifiable. Inflation may or may not be falsifiable, and that's the problem with people like Steinhardt, who
right.
also Ethan has expressed, some sincere criticisms for. But I think what Ethan's maybe misappropriating is that Roger's going to take the Nobel Prize, fame or whatever, and then apply that and say everybody believe in conformal cyclic cosmology. That's not the way science works. I think Ethan knows that. I think he's very, very staunchly in this realm that inflation is right. It's been proven. When, again, inflation, as I always point out, is not the same as the Big Bang. It's not the beginning of time. Inflation is a paradigm that explains most successfully when considering as a formation of structure, not as a theory of how the cosmos came to be. For that, even people like Alan Guth and Andre Linde say that you essentially need the multiverse hypothesis. And then the question is the multiverse, more plausible than the conformal cyclic cosmology? Right. I think it's healthy to have alternative ideas. And Roger's the most creative. He pointed out major problems with inflation, such as the entropy problem. How do you get to extremely low entropy so that nowadays you have really high entropy? He was the first to really point that out. And yes, he's kind of outspoken about it, but he's a treasure. And I think I, for one, we're not going to listen to him just because he won the Nobel Prize and all of a sudden he's right about everything. That would be extreme halo effect.
Right. And I couldn't agree more. So before I leave this, though, I don't want to give the wrong impression of what I was trying to say. I just want to read this one part because this is the part that I was trying to find. The predictions that he's made are refuted by the data, and his claims to see these effects are only reproducible if one analyzes the data in a scientifically unsound and illegitimate fashion. It doesn't say what that is. Hundreds of scientists have pointed this out to Penrose repeatedly and consistently over a period of more than 10 years, who continues to ignore the field and plow ahead with his contentions. So that's what brought up bring this subject to begin with. It's this idea, and much like what Fred Hoyle, I think he also uses this in his article as an example, really hated the Big Bang and couldn't really. Couldn't really. The observations clearly overweighed what his attempts at trying to make the Big Bang go away, and I think he was trying to draw a parallel between that thinking from Fred Hoyle and what Penrose is doing now with this CCC.
Yeah, of course, Hoyle deserved the Nobel Prize for his work on nucleosynthesis and stars. And because he criticized the dominant paradigm, and he actually criticized the Nobel Academy, which is a real no-no, which suggests, my chances are very limited to infinitesimal. I may have a singularity of exactly zero chance of winning.
You've made too many enemies. Yeah.
So I understand completely that argument. But on the other hand, what would you do? Stifle it? And Ethan's wrong in the sense that it's not like Roger's going to slip things past the editors at Physical Review because now he's got a Nobel Prize. I mean, look how many Nobel Prize winners have gone into ignominy. This guy Tim, what was his name? Tim Smith, or he's the biologist who complained that women are no good in the lab and then just ridiculous. He was forced to resign. Try getting a paper published after that. Or Jim Watson, for all the kind of questionable, if not purely odious things that he said about, different races. And William Shockley, of course, felt that
Right.
African Americans were inferior and should be eugenically dealt with. It's just terrible. So I don't think Ethan should really worry that because he won a Nobel Prize for work in numerical and in mathematical relativity, that he's all of a sudden going to slip all these articles past the goalpost. In fact, as far as I know, the papers that he submitted have not been accepted. They've not been published. He gets attention in like New Scientist magazine, but that's not a journal. That's not a scientific journal. That's it's like Scientific American. It's important. It's popular. It's relevant, but it's not a scientific. There's no peer review that goes into it. So Ethan should rest assured that because he won a Nobel Prize, it's not like we're going to start teaching conformal cyclic cosmology in every undergraduate cosmology class. That's not likely to happen. But I don't think we should suppress it either. In that, it's not like teaching the controversy, and we should teach, creationism.
No.
Instead, it's something that's an interesting
false
idea.
Equivalence.
Yeah, it has many, many appealing points about it. But as Ethan points out, it's been refuted. It hasn't been published. And let him continue to go and work on it. And if he does come up with something, we should pay attention, not because he won a Nobel Prize, but because he's extraordinarily creative and has had tremendous insights in science. But we're not going to just blindly accept what he says, thanks to his winning the Nobel Prize this week.
Excellent. Yeah, that's a good point. Okay, I want to leave it there. I know I've got to go, but I just wondered, do you have time for this quick question from Neil?
Yeah.
Who's asking, what do you think about Neil Turok's anti-universe, antiverse ideas?
Yeah, those are really cool. So from one Neil to another, Neil Universe. Exactly. That's a really interesting concept. It kind of parlays with some of Neil Turok's ideas in the early 2000s, what was called the ekpyrotic universe, which is another form of cyclic or collapse, contraction, expansion universe. In this case, you have an anti-universe and a universe that are created at the same time in a certain sense, and that conserves certain symmetry, preserves certain symmetry properties that physicists are very fond of. Conserves energy conservation. There are certain momentum conservation, things like that. I do believe it requires membranes or extra dimensions in order for it, at least in its original incarnation, to be sustained. I think it's an interesting idea, just like the ekpyrotic was interesting, but interesting in the same way Maldaceno's ideas are interesting in that they might give you insight into quantum gravity, they might give you insight into inflation, they might give you other spin-off, side ancillary benefits from studying them, even if there's not necessarily a superiority advantage of them over inflation or over the Big Bang singularity. So I think they're worth studying. It's very interesting, but it may also eventually have to be appraised by the same tools that we appraise things like the ekpyrotic universe and the conformal cyclic universe. So it may, if it doesn't make testable predictions, it may not be really incredibly valuable to cosmologists to pursue. But I think right now it's an interesting purely theoretical topic to explore.
Cool. All right. Thanks for the question, Neil. I appreciate that. All right. Well, Brian, any closing thoughts before we go? I have had you for my full hour here. So
yeah,
any closing thoughts?
I really enjoy it. Yeah, and we should get back together. I'm going to have some great guests coming on my podcast in the next few weeks. I have Nobel Prize winner Frank Wilczek coming on my podcast in a few weeks. He's got a new book out. I've also got a podcast scheduled with Akarni Hamed at the Institute for Advanced Study, one of the most brilliant people in the world. I'm doing a live stargazing event with Adam Rees in November. And
no way.
Friedman.
Oh, that sounds fun.
We're going to do another live stream, perhaps also with Becky Smethurst of Dr. Becky's YouTube channel. So please subscribe to my channel, Dr. Brian Keating, and hopefully Tony and I can continue to. Yeah, so let's keep these conversations going. It's going to be an exciting couple of months on my channel. I hope you all agree. And I also had the honor and privilege of being on Eric Weinstein's Portal podcast. So look for that coming hopefully soon, although he's pretty backed up on his podcast.
Believe me, I feel his pain. It takes me a long time to get my podcast put out too. So, all right. Well, Dr.
Great,
Brian Keating,
Tony.
thank you so much as always for taking some time out to talk with us. We'll have lots of cool stuff to talk about coming forth in the future. I want to thank all of you guys for your patience today and helping me with my new setup here. Hopefully, I'll get the kinks worked out eventually, but not really, because deep astronomy and technical problems is just what we are. So anyway, I will be streaming tonight on the Clear Skies Network on Twitch if you want to check out a rambling stream that I will put together as I speak. So I'll talk to you guys tonight on Twitch, 9 o'clock Eastern Time, Clear Skies Network. On behalf of Dr. Brian Keating, I'm Tony Darnell. Thank you all so much for watching. And as always, keep looking up.